welcome back to cs267, and I think we'll go ahead and get started now. So today I'm going to talk mostly about sparse matrix vector multiplication, spmv as we call it, and a little bit about iterative solvers. Some of this, I'll try to touch on some things you've heard about in, say, Jim's lectures on sources of parallelism, and maybe some things you're familiar with from other courses, but then also hopefully tell you some things that you didn't know about sparse matrix vector multiply and how to optimize it both for parallel and for serial machines. So I'm going to start with a Nobel Prize. We like to remind people of all the different Nobel Prizes that are associated with scientific computing work that has come up in this class. And this one is actually a Nobel Prize in economics, Harry Markowitz, who said, our models strained the computer capabilities of the day. This was in the 1950s. And he observed that most of the coefficients in the matrices were zero and the non-zeros were sparse. And so I think that people credit him with the phrase sparse matrix and the ideas of only storing the non-zeros in the matrix, which came up first. Also, by the way, if you read some of the interviews with him, will say this was some of the most complicated programs that anybody wrote at the time were in these sparse matrix programs to keep track of the bookkeeping of where the non-zeros were. And I think that's still, these are still some of the most complicated scientific applications we write when you have, especially when you have sparse matrices that are changing dynamically. All right, so what's a sparse matrix? You've certainly seen pictures of this in Jim's lectures and in other overview lectures and so on. But it's a matrix in which most of the entries are zero, and that means much greater than 90% typically are going to be zero. And exactly how many of them are non-zero is going to depend on the problem that you're solving, the size of the matrix, and so on. And we're going to represent these representing these kinds of sparse matrices using a dense matrix is going to waste not only memory, but also computation, because you're going to do a lot of floating point operations to multiply a zero by something when you're doing, say, a matrix vector multiply. It comes up in a whole bunch of different applications, in not just in scientific simulations like climate modeling, but also in analyzing images, in things like page ranking for analyzing the connectivity of the web, and then trying to figure out which are the highest priority pages, and in various kinds of graph algorithms, including graph neural nets, which Yelick talked a little bit about last week. So some examples of patterns that you see in sparse matrices would be, the simplest one would be a diagonal matrix. So here we just have non-zeros along the diagonal, and a tridiagonal matrix. And Jim talked about this when he talked about structured grid. So if you have a one-dimensional structured grid, you just have a neighbor to your left and a neighbor to your right. And if you think of that operation, say that relaxation operation, as a sparse matrix, or you construct a matrix that when you multiply by it does that sort of nearest neighbor relaxation, that turns into a tridiagonal matrix. Other kinds of diagonal matrices also come up quite a bit. If you had that same sort of relaxation algorithm on a 2D mesh, you would have a pentadiagonal matrix, and 3D mesh and so on, you would have more and more diagonals. So you can also have matrices that have block structure in them. So here's a matrix that has little 2x2 dense subblocks. These come up often in finite element problems where you have multiple degrees of freedom. You also have symmetric matrices. So all these different ones could also be symmetric, and you may take advantage of symmetry when you're storing the matrix by only storing half of it. And then you can have much more irregular sorts of sparse matrices. And these tend to come up in some problems such as social networks, linear programming, and some of these other applications that are not focused on a matrix that's talking about physical laws, because physical laws tend to have a lot of locality in them and some amount of structure in them. But that's not a hard and fast rule, just to give you a sense of where some of the more irregular matrices come from. And here's some pictures. I think Jim may have shown these. This is the internet connectivity matrix. So it looks pretty unstructured, but you can certainly see some blocks around the diagonal. That means that there's certain groups of websites that will point to each other a lot, or maybe this is actually in the network itself, but you'll have these cliques of networks. Structural design, you'll see a lot of structure when you're looking at something like a physical structure that you're simulating. And linear programming, on the other hand, can have some other kind of weird structure, also may not be a square matrix, but a rectangular and short wide matrix. Recommendation matrices that would come up in machine learning problems, in product prioritization, ad placement, things like that, where you're saying we've got a bunch of people, that's the population, a number of different products, and we have a certain amount of information about which person likes which product, but we certainly don't have a complete and dense history. And Aiden talked about how you might use these kinds of matrices in machine learning algorithms that would, for example, give you information to fill in the rest of the matrix structure. In image analysis, a problem such as image segmentation, you might be looking at computing an eigenvector of a matrix. So here's an input image and the sparse matrix that results from it. So the sparsity structure then says, what is the likelihood that 2 pixels belong to the same object? So when you take that 2-dimensional image and you linearize it, you end up with a lot of structure around the diagonal, because 2 pixels are most likely to be in the same object if they're nearby each other in that image. But then the colors and things like that will also affect the probability that these 2 pixels are in the same object. And then when you compute, you use a iterative solver to compute an eigenvector, you get the structure that's on the right. So a lot of other applications, I've mentioned Google PageRank, so graphs that come up, transportation networks would be another place where you have large graphs, text analysis, where you're looking for topics in a document that is, and trying to figure out, you might be computing the singular value decomposition of a matrix which contains a bag of the words, all the words that appear in that text. Scientific and engineering applications, so certainly in solving differential equations, PDEs, and optimization problems in a lot of other places. So that's just a little bit to remind you of why we care about sparse matrices. I'm now going to talk a little bit about matrix formats and the serial sparse matrix vector multiply algorithm. So for those of you maybe more familiar with thinking about data structures for graphs than for sparse matrices, we often talk about the adjacency list representation of a graph or the adjacency matrix representation. So really that sparse matrix representation can just be that adjacency list or adjacency matrix representation. So here it would be in a linked list, sort of adjacency list representation. So it's a nice data structure for if you want to be able to dynamically create or change your graph, because you can easily remove vertices or edges from something like this, from some data structure that looks like this. On the other hand, not a very good representation when you care about caches and you're going to run down this thing and do a matrix vector multiply it. You don't want to be walking down a linked list if you don't have to. And so we'll instead use an adjacency matrix sort of representation, but then packed into arrays. And so we have our an array that keeps track of where each one of the rows starts, and then an array that has the adjacencies in it and the weights on those adjacencies. So the adjacencies what we call the column IDs in a compressed sparse row implementation. So that tells us what vertex that is corresponding to, and then the weights are the weights on the edges. And there's the sparse matrix version of it, sort of blown up as a dense matrix. And then this compressed version of it, compressed sparse row representation. And we can store both directed and undirected ones. If we have an undirected graph, that's going to turn into a symmetric matrix, because every edge, of course, has its opposite edge in it. And then we may decide, once again, not to store all of those, both the redundant edges, if we've got a symmetric matrix. So how we're going to write a compressed sparse matrix vector multiply? Well, let's look at this compressed sparse row representation, and let me look at the representation a little bit more detail. So we've got to keep track of how many non-zeros we have in this. We haven't shown that in the picture here, but the length of the values array and the length of the index array, which will be the same, will be the number of non-zeros, n and z. And then there's an array of the val array and the index array, which are shown. And then the last thing is this array that we saw in the previous picture too, which is the row start pointers, or sometimes just called the pointer array, that says where each one of these rows starts in the sparse matrix representation. There are a lot of other storage formats that come up in practice. Compressed sparse row is one of the more common formats, and we're going to mostly focus on that today. We'll talk a little bit about some blocked formats and things, but part of this is just to make this this lecture concrete. And so we're not sort of talking about a lot of different formats. I will mention some other ones though, but some that are common. You can certainly have compressed sparse column format, which looks just like compressed sparse row, but stores things by columns instead of rows. Coordinate format stores a non-zero and a column index as well as a row index for each of the non-zeros. So in compressed sparse column, you would store just a column vector, and then you would store an index that would represent the row that non-zero comes from. In coordinate, you have both a row and a column index. So this is, again, a data structure that's easier to modify. It's easier to add non-zeros to it in the sense that you don't have to worry about necessarily keeping things contiguous in memory and moving things over in order to make space for them. And there's a question about whether compressed sparse row is represented differently for directed and undirected graphs. And it doesn't have to really be a different representation for the undirected case. I mean, what I showed you was, first of all, a directed graph, which is sort of the more general version. The one thing you would do in an undirected graph is you might cut down on some of the non-zeros in each row. You wouldn't store the ones that were in the symmetric upper half. So it would be the same representation data structure, but you would store a smaller number of non-zeros because you know that each one has a symmetric version on the other side. Now we can also take advantage, as I said, of symmetry, but then also blocking. And there's a couple of different kinds of blocking that we'll talk about. One is register blocks, and this is where the blocks are very small and actually very and dense. So there will be all non-zeros in there, or we'll even in some cases fill in explicit zeros so they have the same size. And these would be things like 2 by 2 or 3 by 3 or a 2 by 3 matrix blocks, where we don't have to store then an index for each non-zero. So that's going to be one of the big advantages of it, is that if you have a matrix that naturally has some blocking structure, you can actually cut down on the amount of storage because you don't need so much index overhead if you only store an index per block rather than an index for each non-zero. And cache blocked matrices are going to have much larger blocks representing the reflecting the size of the cache, but those blocks are going to be sparse themselves. So you don't want to blow up a cache block into a dense representation because most likely you'd have too many zeros in it that you'd have to fill in. And you can have a lot of other specialized representations that people use in various scientific and non-scientific problems, depending on what the structure of your matrix looks like. You can take advantage of that structure and make something that's more space efficient and then more time efficient as well. All right, so let's talk about SPMV in this compressed sparse row matrix. And here we've got, once again, our data structure. And I've drawn the matrix A here on the left with the source vector and the destination vector on the top and on the side, because even for a dense case, what I'm going to want to do with each one of those elements of the source vector is use it to multiply everything in the column of the A matrix. And of course, each one of the elements of the Y vector is going to get updated by everything in the row of the A matrix with a dot product times everything in the X vector. So that's why we draw it this way. And I think you've seen that before from in other lectures by Aiden at least, and probably by Jim. So here's our sparse matrix vector multiply kernel. And it looks a lot like the dense matrix multiply. We're going to run through each row. And then rather than running through each index j, so rather than I and j, we'll use an index k, which is starting at the pointer, the ith pointer. So each one of these, right, the pointers tells you where, in what index location that row of indices starts and where the row of values starts as well. And so then in the inner loop, you're just multiplying it times the value that is at that location k, but then also the x value that is at the index at the position k. So there's this indirection in here, and that's going to cause problems for the compiler, and it's going to cause problems for the hardware in terms of that indirection causing you to jump around through the x vector quite a bit while you're doing the matrix vector product. And so this is also a BLAS2, not a BLAS3 operation. So there's no reuse of the A matrix. And that's really true whether this were a dense or sparse problem. It's already going to have very low computational intensity just because it's doing a matrix vector multiply rather than a matrix matrix multiply. But what this means is that the maximum reuse, as we've written it here, is really, sorry, we're getting maximum reuse of the elements of the Y vector because we're going to read the Y vector. Even though it's written here in this inner loop, Y sub I doesn't change in this inner loop. So we could really use a temporary here for the YI values on both the left and the right. And then we're going to, so we can store that value in a register and just read it once at the beginning of the, for each iteration of the outer loop and write it at the end of that inner loop. And so we've got the maximum reuse that we can possibly have in this for that Y vector. And the problem then is, can we improve the reuse of the X vector? And we can try to do that by, for example, if we've got two non-zeros that are in the same column, those are going to need the same value of X. But you can see that as we've written it this way, when we go around the corner, it's very likely that value is certainly not going to be in register because the compiler can't figure out which of the X values are in register and which ones are the same because of the indirection vector. And the cache may or may not still have it in sitting in cache. All right, so that's the basic serial algorithm. Next, we're going to talk about how to parallelize this, and for both shared memory, a little bit on GPUs, and also on distributed memory. So it's not too hard to take this code and then turn it into something that will work in an OpenMP, for example. And so here we're just, we've put in these OpenMP pragmas and said that some of these index values, for example, J and I, and the temp value are going to be local to the processor. So this temp value then is reading in that index of J. And so that will help the OpenMP compiler do the code generation for it, and not worry about race conditions, for example. And so this code doesn't have any race conditions because each one of the processors is accessing a different subset of the elements of the Y vector, which is where all the writes are happening. Now this one is scheduled statically, so I've said static schedule this. So there's a problem with that, of course, which is that the number of non-zeros in each of these rows can be quite different, and therefore some of the inner loop, the threads, the OpenMP threads that are running one of these inner loops is going to run much longer than another one. So you might want to instead use a dynamic scheduler here. And I won't read through this, but this is what some code from a previous GSI in the course, David Sheffield, actually maybe in the undergrad version, wrote out what this looks like for a SIMD optimized code. And once again, you're iterating through all the rows, this top orange highlight here, the yellow highlight in the code, the 4 int 32 of I. And then there's an inner loop, which is blocking it into groups of 8 for a SIMD width of 8. And then you have to do a gather. And so that is actually using a gather instruction in order to do this. So, and then there's a little bit of cleanup code because in each one of these, in case the number of columns doesn't divide by the vector width, then you have to make sure you do all the remaining ones at the end. So, and this is what it looks like in CUDA. And so here's our global SPMV kernel that's can be called in CUDA, and it's taking in the same sorts of data structures. And this is going to get also parallelized over the inner loop. The other thing you often want to do on something like a GPU, because you're looking for a lot of parallelism in case the CUDA compiler can't really parallelize over both of these loops simultaneously, and it may generate this code, but is really to do a segmented scan sort of operation where you're doing so you've got these independent multiplies of the gathered elements from the X vector and the multiplies times the values of the sparse matrix, those value elements that are in that one vector of the sparse matrix representation. But then you need to do a reduction because you need to do the dot product, the add part of the reduction. And rather than doing that sort of one row at a time, you can do it across a whole chunk of rows, but in a segmented way where the adds stop at the end of each row. And so you can implement this also using a segmented scan. Here's a little bit of what that algorithm looks like. We've got these, here's the indirect reads of the X vector into a vector that's of the same length of the number of non-zeros. And so here's our X vector up here. It just happens to have 1s and 2s in it. And when we fill in this X of ind vector, then we're reading these out using that gather sort of operation. And then we compute the products completely in parallel. So that's an embarrassingly parallel operation, if you will. And then when you want to do a reduction on that, you need to calculate the endpoints for each one of those rows in order to make sure that the sum scan then is stopping at the end of each one of those rows. Something that is also, it can be done on OpenMP, but is also popular on GPUs would be a diagonal format. This is because a lot of matrices do have non-zeros that are striped in diagonal patterns across the matrix. And here it's a tri-diagonal, but as I said, you'll see pentadiagonal or whatever for different dimensionality of, say, meshes with nearest neighbor computation on them. And so this kind of diagonal format, what you can do is store these diagonals now as a vector but then pack them in a two-dimensional array. And you have to, and there's some padding of zeros in this case because the blue diagonal, of course, is a little bit longer than the red and the green. And so here's some code in OpenMP in order to make this diagonal format work for spmv. And as I said, it's also popular for GPUs. And there's also sort of what are called jagged diagonal formats where if your diagonals really have very different sizes, what you might do is sort the diagonals by the different sizes and put them into groups and pad them out for a set of diagonals that are roughly the same size. So you don't have too many extra zeros padded in there. And then separately have loops that work on the different chunks that have very different sizes. And by the way, you can also use things like segmented scans to help optimize those kinds of things on GPUs. All right, so let's talk about the distributed memory case. And I'm going to first start up just to remind us of what the dense matrix vector product looks like. And this is, you saw this when Jim talked about dense linear algebra, at least dense matrix multiply in parallel, things like that. But let's just remind ourselves. So here we've got our dense matrix A, and let's say that we've just got 4 processors, and each one of the processors has one chunk. In this case, it's a block row layout. So it's a one-dimensional algorithm, which is dividing up the A matrix in just one dimension. And I've drawn again my X and my Y vectors there on the side and the top. And I'm assuming both of them are also partitioned in the same way. That is, each processor owns some contiguous chunk from 0 up to 3 chunks in each of those. And one of the reasons, by the way, that we tend to draw it this way for the X vector looks this way is because oftentimes we are going to run an iterative algorithm in which the X vector is some function of the Y vector from a previous iteration. And so sometimes you'd like to say, well, I'd rather just have my X vector replicated over all the processors. And that's something we're going to actually do inside of the algorithm, but we don't start with it replicated because it often comes as an output of the Y vector, maybe not the Y vector itself, but some function from, say, scaling the Y vector, applying various operations onto the Y vector. And that's why we have the same sort of partitioned layout here. So in this algorithm, which has a row major layout and a block row distribution of the A matrix, then what we can do is just broadcast down the different pieces of the X vector. And we can do that one at a time, or we can do all of the broadcasts at the beginning, and then all of the work after that is completely local. So there's just local, say, dot products in each one of these row submatrices, or in compressed sparse, in row major format, and all the work after that initial broadcast is independent. And on the other hand, if we store it in a column major format, we don't need to do any broadcast because each processor only needs the X vector elements that it already has. But in order to compute Y, now we need to do a reduction across the rows. And so this one is going to use this, let's say that we've stored it in rows within each processor. Once we'll just do DAXB operations, say, across each one of those, but then we'll have a local temporary that we accumulate Y into, and then all the processors will add their values of Y together. So this is, and we can have a two-dimensional algorithm. And this two-dimensional algorithm is where we divide the A matrix A up in 2 dimensions. And we're going to do we're going to do both a broadcast and a reduction, but each one of those will be, say, square root of P in size. And so in a large number of processors, this will improve the latency because we'll have 2 square root of P operations rather than 1 order P operation for the communication steps. And so this two-dimensional algorithm can be also very useful for that. Now it's useful for the dense case. For the sparse case, let's see what happens. So if we can really use the same algorithms here, and inside them, each local operation is being done as a sparse operation. And so if we've got this block row partition that we talked about before, we could do what we did exactly in the dense case, which is just replicate X across all of the processors. So we can broadcast the chunks of X down, or we can say, well, if this is a really sparse matrix, and for example, let's say that the non-zeros are actually clustered around the diagonal, which is not the way this picture looks, but let's say that they are, then maybe A0 doesn't actually need P3 or doesn't need very much of P3's X vector. It only needs a little bit of it. So you could save on the volume of data sent if you just pack up exactly what is needed. Whether that's a good idea depends a lot on your sparsity structure of your matrix, and it's going to depend on the size of the machine and basically the chance that you need everything. It certainly is going to create more overhead to both communicate with the other processors which chunks of X you need, and then to pack them up. But you may save on the communication volume in the end, depending on how sparse the matrix is. And it'll depend, as I said, on also whether they're clustered or distributed evenly. So we can also use a similar kind of column algorithm in which we're doing basically sparse matrix vector multiplies locally with data that we entirely own, but then we still need to do a reduction across all the processors to compute. So we have a temporary value of Y on each one of the processors, and we add them together in order to get this other Y, and maybe we need to partition it if we're going to use it then for the next iteration of X in some form. We can also do those reductions sparsely. That is, if we really don't have very many non-zeros in that, we might not want to construct, or at least we don't want to communicate the entire dense vector Y, but you can imagine this now makes the reduction operation significantly more complicated in terms of implementing what that sparse reduction looks like. And we can use the 2D algorithm, and this is especially useful when the non-zeros are uniformly distributed across the matrix. Or said another way, this is not a very good algorithm if the non-zeros are going to be clustered, say, around the diagonal, or they appear anywhere in the matrix in big clusters that will cause the number of non-zeros per processor to be very different. Now, another thing you can do in a sparse matrix algorithm is not use exactly n over p if n is the dimension of the matrix, and you can try to slide these lines around a little bit in order to give you better load balancing if you have a cluster of non-zeros someplace in the matrix, although that can get quite complicated unless you leave the lines as completely connected vertically and horizontally. But each one of the blocks doesn't have to have the same number of rows or the same number of columns, but you typically do want it to be the same across the different blocks in order to make, say, the reductions and so on work well. So this is used in, there is a benchmark that was actually very popular, and I'm going to talk more about another benchmark today that's being used more actually as part of the top 500 list. The older benchmark was from the NAS parallel benchmark suite, and it's called the NAS-CG or NAS conjugate gradient benchmark, and it's running the conjugate gradient algorithm, which is an iterative solver on one of these sparse matrices. And in this particular benchmark implementation, it constructed a random non-zero pattern for the matrix, which is a nice and convenient thing to do in a benchmark because you don't have to worry about reading in a specific matrix. It allows it to scale up and down with, say, the size of the machine that you want to run on and things like that, but is not very realistic for what most physical simulations look like because the non-zero pattern typically is not going to be randomly distributed. And so, as I said, this parallel 2D algorithm is not very good if the non-zeros are clustered. So, in this parallel implementation, and let's talk about, it doesn't really matter. Here we've just got our 4 processors and something like a compressed sparse row or block row distribution of the distributed matrices. The best non-zero pattern we could have for this would be a block diagonal matrix in which each processor would just have non-zeros in the block that it owns. And what that means is it could completely do the multiplication locally, right? It has the X vector that it needs, multiplies it times its little green sparse thing, and then it does the update into the Y vector, which is completely independent. And then that Y vector could be used again for the next one. Now, it's not a very interesting problem if all you have is local work that's going on, but you can have problems in which the non-zero structure approximates this. And so a lot of times what you'll want to do is in a distributed memory setting, you may want to, you don't have an ideal matrix, but you may want to reorder the rows and columns in order to get something close to the this ideal sort of format. So minimize the number of non-zeros who are out here in the blocks away from the block diagonal. So what is the benchmark that people actually use more in practice today? It's one called HPCG, high performance conjugate gradient. So it's still a conjugate gradient algorithm as in the NAS conjugate gradient. It's really dominated by the sparse matrix vector multiply operations. This is a three-dimensional PDE that can be used in things like finite element, finite difference, finite volume problems, things like that. It's got a single degree of freedom. So in a heat diffusion model, which is related to what kind of one of the model problems that Jim talked about in the Sources of Parallelism lecture. And it's got what are called zero Dirichlet boundary conditions. And so that's kind of just putting zeros around the thing to make, you have to figure out what the boundaries look like in these kinds of problems, and a synthetic right-hand side such that we're going to have a solution that's equal to 1. And that just sets it up nicely as something that we can check in terms of the benchmark. And there's a spatial domain, which is going to be globally, it looks like nx times npx. So the processor grid is x by y, so npx by npy by npz, and then there's a nx by ny by nz 3D mesh and each one of the processors. And so this global domain then is the product of those, if you will. And so the sparse matrix, so that's what the physical grid looks like. But now we need to think about, well, what does that turn into in terms of these nearest neighbor sort of computations that happen on that three-dimensional grid with some special cases on the boundaries? Well, we have 27 non-zeros for every row in the interior of the matrix. And the matrix is representing one of the matrix row is representing one of the mesh points in that 3D matrix. And so there's you can see from the picture on the upper right, the 27 points that are all around it, including itself. And then somewhat fewer points when you're on the rows that are the boundaries. And this is a symmetric positive definite matrix, which is important because the algorithm that you're running on that's using SPMV is conjugate gradient, which requires a symmetric positive definite matrix. So this is what the benchmark result looks like for some of the top 10 machines on the HPCG benchmark. And I know this is a very busy slide. So I'll just, if you look at the first two columns here, the first column, which says number on top of it, a hash sign, is the ranking in the HPC benchmark. Now, not every machine on the top 500 list actually runs the HPC benchmark, but most of the top machines do. And so the second number here is what the ranking was in the top 500 list for the HPL, the high performance LINPACK benchmark. And so you can see that some of the machines are the same, right? So the first three machines here, the fastest machine for HPCG is the same as the fastest machine for high performance LINPACK. And what that says is the high performance conjugate gradient benchmark, roughly speaking, is going to measure the aggregate memory bandwidth across the machine, a little bit about the network bandwidth, or at least you could have a machine that doesn't have enough network bandwidth to solve it well. But for the most part, and we'll see this later when we talk about the serial optimizations of SPMV, SPMV is going to be memory bandwidth limited. And so the overall HPC benchmark is limited by the sum of all the memory bandwidths across the nodes. So you can see that there are some machines which are much higher in one than the other, or at least what you see here is ones that are higher in the, say, memory bandwidth, the HPC benchmark, which the NIFS machine, which is an NEC machine. So it's a big vector supercomputer, or based on vectors at least, and it is it's very fast on doing conjugate gradient, but not so as fast. It doesn't have as high a peak performance, and so you can also see some of the peak numbers over here as well. And let me just stop this so that I can, when we look at the others. So the other thing that's sort of interesting to see, this top machine is running at 442 petaflops, right, for the high performance LinPack benchmark. And this is, an HPC is running at 16. So really, really much lower in terms of the flop rate. On the other hand, by the way, it's probably running at peak bandwidth, whereas the other one is probably not running at peak memory bandwidth as it's limited by floating point operations. And so this one is really measuring that aggregate bandwidth, as I said, across the machine. But you can see that most of the machines, after you get past the top 5, are not even running at over a petaflop. So this really shows you, for if you think that a lot of scientific computations are going to be much more well reflected by conjugate gradient than by something like dense LU factorization, that you'll really run at something more like 1 petaflop rather than running at 100 petaflops. And the last thing is just to look at what these percentages of peak. So this is both the percentage of the second to the last column is of the peak, the hardware peak, and the last column is the percentage of the high performance LinPack peak, which you can go back and look at the other numbers to see. You would get the same thing by looking at the difference. So obviously there's some machines that run and where there's a bigger difference, although most of them are actually pretty consistent in terms of and what that says is that the high performance LinPack benchmark actually runs at a pretty consistent fraction of peak, and at least relative to the much smaller fraction of peak, the 1 to 3% that most of these are running at for HPCG. Okay, any questions? Okay. All right, so the next thing I want to talk about that hopefully gives you a bit of an idea of how these are, how you would parallelize this sparse matrix vector multiply algorithm, some of the benchmarks and the speed that you should expect from it, but also then a little bit about the different types of layouts. So now let's kind of drop down into what happens when we're optimizing sparse matrix vector multiply for a single processor or for maybe an SMP node. So one of the things that we'll want to do in some cases is to change the matrix format and to use register blocking. Now you are familiar with the idea of register blocking from homework 1, from using it on dense matrix multiply. You are loading a certain set of things into registers and reusing them as many times as possible in order to get your computational intensity up as much as possible. But this is looking at a real sparse matrix now and how we're going to think about turning that into a register blocked format. So remember though that we're not doing matrix, we are doing matrix vector. So we're still not going to see the kind of rates that you would get in dense matrix multiply, even because we just have one vector that we're multiplying by. So here's a particular matrix that was used as, this is slides from Rich Vudak's thesis from many years ago. So you're going to see a few old machines coming up here. One of the things that we would love to have somebody do is to benchmark some modern processors on some of these different types of matrices. And that could be an interesting final project, looking at the different algorithms and how they perform across the different types of architectures that are much more current. So this is a structural analysis problem, and it has an 8x8 dense matrix substructure to it. And these matrices are sort of, you can see from the previous picture, they're not all on the diagonal, but there are this sort of tri-diagonal structure, if you will, but each one of those is actually a set of blocks inside of those. So this is blowing up one of those diagonal structures. And this gives you a hint that you might want to use something like an 8x8 register block format, because then rather than storing, remember, an integer that is the index as well as the non-zero, so each one of these blue things is some floating point value that I need to store, but I'm also storing an extra integer associated with each one to say, for example, in CSR format, what column that non-zero is in. So I could instead just store, say, one non-zero, one index for each one of the blocks. So when we use this kind of block structure in SPMV, the bottleneck is really the time to get the matrix from memory. And we're doing only 2 flops for each one of these non-zeros. And so the real kind of overarching idea is basically to try to compress the size of the matrix structure so that you're moving less data across the memory bus in order to do the read of the matrix. So we can't help but reading every entry of the matrix at least once, and we only will read it once. So we don't really have any reuse of the matrix, but we can try to make the matrix smaller. So if we store only an index for each one of the blocks, then as the R by C, that is the block dimension, grows, then the storage can drop by almost a factor of 2. This assumes that everything is 32-bit quantities. So that is that we were storing in the original implementation, say one integer, 32-bit int, and one 32-bit floating point value, so single precision. And so it'd be somewhat less, and double precision would be the potential, unless you're storing very large integers, 64-bit. But so that this improves it improves the time to fetch the matrix then from memory. And this does change both the data structure and the algorithm. We have to figure out kind of before we start what R and C are going to be, and we're going to change the layout of that matrix in memory. If it comes in say CSR format, we're going to have to rewrite it into something that's a blocked format. And one of the questions is, how do we decide on the block size? Well, in this case, we looked at a picture and we had pretty good intuition that R equals C equals 8 is the best choice. And in fact, that's what a lot of domain experts, if you're somebody in say mechanical engineering doing finite element analysis and you think you have a good understanding of your matrix, you might say, well, I'll just store these 8x8 blocks as one contiguous block. And that might be better because it will compress the total size of the matrix, but it may not be optimal. So what is actually going to be optimal? Well, in this particular matrix, this shows the different block sizes across the X and the Y axis. So this is the row block size R across the Y axis and the column block size C. So these are the sizes of the little dense matrix subblocks. And what you can see in this is that although 8x8 is certainly better than 1x1, the reference here, which has, and this is showing the megaflop rate, old processors, so this is megaflop rate, and the reference implementation runs at about 270 megaflops, and that's the 1.0 here. And the 8x8 runs about 1.5 times faster, 1.55 here in the upper right, which is great, but nowhere close to the best. The best algorithm is a 2x4 matrix, and that you can see this gets a speed up of 4.09, so it runs 4.09 times faster, and that is that'll give us that kind of effective megaflop rate as well. So that's the best for this particular one. Now, it's not surprising that it's something that is divisible into 8x8, that the register blocks are, and you probably from your work on homework 3 might have some sense of why 8x8 is just too large. You don't have enough registers to hold something like that. Whereas a 4x2, you might be able to unroll that inner loop and load all those things into memory. They're going to be, that 4x2 block will be contiguous in memory, so you can load them. They'll come in through the cache line, and then they're going to get loaded into the registers and used inside of this inner loop. And this is what it looks like to optimize on that same matrix, but a bunch of different processors. And again, these are a bunch of older processors, but the point is that the block size not only depends on the matrix, but it depends on the machine. And so what the optimal block size is does depend on something about the registers or the memory system and how that balances out. And here's some more machines with just more pictures of different kinds of heat maps in terms of what's the best block size. All right, well, that was an easy problem, and already our intuition might have given us the wrong answer that said that the best matrix, the best register block size would be 8x8, when in fact it was not on any of those machines. I think it was a 4x2 or 2x2 or whatever. But a lot of matrices don't block that easily. So you might say, well, we could just look at the matrix structure and maybe that will tell us the right answer. And at least it would narrow things down a little bit. But in a lot of matrices aren't quite that well structured. So here's another matrix that comes from a fluid dynamics problem. If you blow up one of the non-zero pieces of that matrix, in this particular case, it has this non-zero structure, and it kind of looks like 3x3 dense subblocks. And in fact, you can kind of put a mesh around this and you can see that there's lots of dense 3x3 subblocks in it here in the middle, for example, and in a number of other places, those blocks have all 9 points filled in, but there's a bunch of them that don't. And in order to actually capture this and store the entire matrix in a 3x3 register blocked format, we're going to have to fill in the missing, any block that has at least one non-zero in it but isn't completely full, we're going to fill in the rest of that block with explicit zeros. So we'll add in explicit zeros, which will be these red points that have just been added here. And this is surprisingly actually faster, even though you're going to be doing multiplies on all of these little red blocks. And you may think that you've made the matrix bigger, but actually because of the storage overhead of the index structure itself, you've actually made the matrix, that you've compressed the matrix somewhat by storing only one index for each one of these 9 non-zeros. And even though you've made up a bunch of even 50% more non-zeros. So we call this the fill overhead, which is the number, the kind of percentage of or fractional overhead that we need to add in explicit zeros in order to get this uniform block size. So one of the things that Jim and I did a number of years ago with, this was work that was done in Rich Vudek's PhD thesis, was to build a library that is automatically tuned for these kinds of sparse matrices, and it's called OSCI, which stands for the Optimized Sparse Kernel Interface here. And it's different than building something like the BLAS for dense linear algebra, because you don't know what the matrix structure is going to look like in advance. And so there's a certain amount of work that we'll want to do ahead of time, and some amount of work that that is when we install the library, as you would do with the BLAS. So if you were going to build a self-tuning BLAS library, such as Atlas or one of these things, then you can, at the time that somebody, say at NERSC, goes and installs the libraries for that particular machine, it can run a bunch of auto-tuning stuff and figure out what the right block sizes are, register block sizes, and so on for dense matrices. For sparse matrices, we need to also wait and look. We can do some of that at installation time, but we have to wait and also look at what the sparse matrix structure looks like of your, say, your finite element matrix or whatever. So, and this was some work that was done both in Yunjin Im's PhD thesis, and she built a library called Sparsity, and then he came and built the one called OSCI that is still more popular in terms of being used today, and has a much larger set of implementations and things in it. But the basic idea that's in both of the theses is to try to come up with a heuristic for figuring out what the register block size is. And so there's, first of all, a certain amount of offline work that is done, that is at library installation time. Don't know what the actual scientist matrix is going to look like at this point, but we'll compute what's called a register profile for the machine. And that is going to be using a dense matrix in sparse format. So let's say compressed sparse block row, so CSR, but each one of the entries is a little R by C block, and we'll try a bunch of different R and C sizes for a given machine. We've got some time because we only do this once at library installation, maybe once when you buy the machine or whatever, once it's been delivered, but you don't have to do it every time somebody runs an application. And so we're going to run a bunch of different register block sizes. These are also not huge, right? You might go up to something like 8 by 8, but you're certainly not going to be going up to 1,000 by 1,000 or anything like that. And then when you build a table that says what is the megaflop or gigaflop rate that you get for a given value of R and C for a dense matrix in sparse format. So now we have that register profile that tells us basically probably how fast any matrix that is in that R by C block format is going to go, because probably the best case is going to be a dense matrix in sparse format, just because the other cache locality advantages you'll get from that. And then what we'll do at runtime, or when the user wants to solve a particular problem, is estimate how much we'd have to fill in their particular matrix A in order to make it an R by C matrix. And that is done using some sampling, and I may say a little bit more about that, although I want to make sure I have time to get to some of the other topics in lecture. But, and so we at runtime then are going to choose RNC to minimize the fill overhead divided by the megaflop rate. And so that's estimating basically the inverse of the megaflop rate that we're going to get on this machine of sort of real megaflops if I only counted the flops that were in the original matrix, not the extra, zero flops that I have to do because I've filled them in for the R by C. So this fill factor is going to estimate sort of how much extra work that we're doing, and then the megaflop rate tells us how fast it'll go. And so this is what a register profile looks like for one of these older machines. This is Itanium 2. And what you can see from this is, you mostly want to use relatively small block sizes. Here's that that 2x4 matrix you can see is probably the best case that you're going to get. And so that tells us this is a dense matrix in sparse format, but this is also the result that we got for that Rafsky matrix, which didn't have any fill overhead, right? So it's not surprising that that's the best that we're going to get here. Now, if we tried to use a 12x12 for Rafsky, we would have had, not only would it have been running at a slower rate, but it would have had a lot of fill overhead. And this is what the register profiles look like for a bunch of other machines. And perhaps the most important thing to recognize is that there can be a huge difference between the optimal one and one that's off by a little bit too large, for example. Even a little bit too small, you can see you'll really drop significantly in performance, but especially if you make the block size a little too large. And that's shouldn't be surprising to you, because you understand that once you've made the size of that block too large, it won't fit in registers, and the compiler is going to generate a bunch of spill code in order to make that little inner loop work well. And there's some more heat plots, and Appendium has a much more sort of stable heat plot, but also has a little bit less performance advantage overall. Okay, so as I said, and I think I won't read through the details of this, is just to say that it is expensive to compute the fill overhead exactly for a given matrix and for every possible value of R and C of interest. And so instead there's a sampling algorithm that's used inside of OSCE in order to estimate what the fill overhead is. By sampling a bunch of the rows and columns of the matrix, you can get a pretty good estimate of what kind of fill you're going to be looking at in order to use that representation. And we're trying to, by the way, make the cost of tuning equal to about 10 SPMVs or something like that. And why is it okay to spend that much time tuning? Because in most applications, we are going to run SPMV over and over again. Usually that's going to be on the same matrix. And even if it's not on the same matrix, even more frequently, it's going to be at least on a matrix that has the same structure to it. And even if you don't have exactly the same structure, if you're working in a particular problem domain, let's say you're doing finite element modeling of buildings or something, that over a period even of a year, you may be using a bunch of different matrices for different structures, but their non-zero patterns will have a lot of similarity. So built into OSCE is also the idea that you can kind of remember from previous runs what is the optimal setting. You then have to be sophisticated enough to know that it's time to retune it if you're going to really substantially change the types of matrices that you're working on. But it is, you can spend some non-trivial amount of time tuning because of the fact that you plan to do lots of matrix vector multiplies. Here's some references to also the idea of using machine learning to search through the optimization space, both for dense and sparse matrices. I think there's probably even a number of more recent papers, but here's are some pointers if that's something that you're interested in looking at. It has been something people have looked at in other class projects. So how well does this heuristic work inside of something like OSCE? Well, what we're seeing here is doing an exhaustive search on a bunch of different block sizes, at least sort of reasonable block sizes. And what we have across the x-axis is different matrices. I'm sorry, some of this got overwritten here on the bottom, but these are just matrices that are numbered from 1 to 24. The leftmost one is the dense matrix in sparse format. The next is finite element matrices with and without variable coefficients, and and then the other kinds of matrices, and at the right are some of the hardest ones, which are the linear programming matrices. And the hardest ones in terms of getting good, they don't have very good structure in them, and therefore they're going to run at a lower percentage of peak. And this says even if I don't use the heuristic, if I just try all the possible kind of sensible block sizes, this is the kind of speed up I can get. Not surprisingly, the dense matrix and sparse format gives you the best performance overall. And the others have to fill things in, for example. But what this says is that the heuristic, which is the green box here, is getting actually very close to the optimal case. So there's a few cases where you lose a little bit of performance from the heuristic rather than doing exhaustive search, but it's much faster to use the heuristic. And so this proved to be an effective way to find the block size. And just for reference here, this is a dense matrix in dense format. DGEMV is on this particular machine running just over 1.3 gigaflops. So again, this is an older, this is an Itanium 2. And what you can see here is the dense matrix in sparse format is actually getting surprisingly close, but that's because you're using large enough blocks that you only have the indexing overhead, say once for every 8 elements, a 2x4 dense register block in there. So that's why it gets pretty close to the if you just store the whole thing as a dense matrix. All right, now an obvious question you might have from working on homework 1 is what about cache blocking? And first of all, for matrix vector multiply, whether it's sparse or dense, you don't tend to get nearly as much benefit from cache blocking. In fact, you may not see any at all. And the reason is because you don't have any reuse of the A matrix. You only have reuse of that X vector. So what you're looking at, let's say that we're doing a sparse matrix in CSR format, just to make your intuition concrete. So we're doing dot products across the rows. And we're worrying about how it's using the cache. Well, the problem is going to be if that row becomes very wide and there's non-zeros kind of spread throughout the A matrix, the non-zeros throughout the A matrix, then when you go around the corner to the next row of the matrix, things will have been kicked out of cache. And so in order to, if you're looking for a problem, which we were, by the way, and this is some work that Rajesh Nishtala worked on in his master's thesis a number of years ago, was what's a problem that will really benefit from cache blocking? So what are we going to do in cache blocking? We're going to chop the matrix into sparse blocks, so we'll make them smaller matrices, and so we get better reuse of the X vector, and that's really all we're optimizing for is reuse of the X vector. So a problem that's going to have the most benefit is one that doesn't have much structure in it. It's got non-zeros sort of uniformly distributed throughout the matrix. Also tends to be one that's very wide, because then it has a very big X vector when you're multiplying times it, and then so for these sort of short wide matrices with very unstructured non-zero patterns, cache blocking can be helpful both in the serial case, and I'll show the results, which are actually work by Yunjin Im on shared memory multiprocessors. So there's cache blocking on the latent semantic indexing matrix, one that doesn't have much structure to it. So here there is a speed up of about you get about 4x from doing this kind of cache blocking optimization. And so maybe, yeah, this is in this 2007 paper, and the title of the paper should kind of give you a hint as to how successful this was in general. The title was "When Cache Blocking of Sparse Matrix Vector Multiply Works and Why," and so it was because there were many cases in which it didn't actually work. And here's another, these are synthetic matrices that now that have random matrices, but they have particular structure, which is they're banded. And this shows 4 different random matrices with this sort of banded non-zero structure that's random within the band. And this was also used in Rajesh's paper and Nishtala's paper. Okay, so I haven't gone through all of the different optimizations, but there are a lot of different things that you can do for serial performance optimizations, many of which are going to be important on SMPs as well. And I'll say a little bit more about that. But there's register blocking, which we talked about in some detail. One of the things that you can do is to split the matrix into different size blocks. So variable block splitting would say, maybe I've got part of the matrix that looks like 3x3 blocks, but then I've got a bunch of things left over and I don't want to fill all that are just isolated non-zeros. I don't want to fill all of those in with explicit zeros, because that would create too much overhead. So I can make that matrix be the sum of two matrices. One has a nice block structure and the other has sort of everything else left in it. And it may have a different block size. And you can store them in diagonal format. You can do reordering. You take advantage of symmetry, and you can see here the speed up numbers for each one of these different kinds of optimizations. Multiple vectors, which is where the second matrix, the vector is not a single vector, but a set of vectors. We also might call this sparse matrix times dense matrix multiply, but the second matrix is say tall and skinny, then you end up with this, you can end up with a much higher speed up. So now this is the last one, this multiple vector case is the first example here on this slide in which you're actually you get some reuse of the A matrix itself, not just of the X vector or the Y vector. Other kernels like sparse triangular solve, and something that will come up at the end when I talk about iterative solvers, are higher level kernels, not just multiplying times multiple vectors, but also computing things like AX, A squared X, A cubed X. Also A times A transpose is very common in a number of different kinds of algorithms. And so optimizing that combination rather than just implementing A times A transpose times X as A transpose X and then A times X, you can try to optimize for the memory hierarchy across it, getting some, again, all these things on the right also have some amount of reuse of the A matrix elements. And so, and Jim put another link in the chat if you want to see that on another piece of work on auto-tuning in terms of auto-tuning in parallel applications more broadly, not just sparse matrix vector multiply. So what happens if we look at the roofline for SPMV? And this is work now from Sam Williams' thesis looking at 4 different architectures here. The fourth one, something that's a dead architectural model, actually maybe a couple of them are Victoria Falls, which was maybe kind of looks like things that we see today. But anyway, the cell blade processor in the cell processor was one that actually one of the large HPC systems in DOE ended up having, and I think partly influenced by these results, which is if you really optimize the code, we're going to see some pretty good performance that you can get from this. Notice all of these graphs have the same y-axis, so you can also compare across them. But if you just sort of take matrix vector multiply, sparse matrix vector multiply out of the box and run it in, say, OpenMP, I think this may have actually been a pthreads implementation at the time, you get pretty low fraction of peak performance, certainly, but you also get something that is kind of pinned to not a very good bandwidth curve. So there's multiple bandwidth lines on some of these roofline plots, and that has to do with the memory system having, say, multiple streams, because you've got a non-uniform memory system with different groups of memory associated with different cores, for example. And if you haven't optimized things well for that, you're going to run at this lower bandwidth peak, but you're sort of pegged on that lower bandwidth number there for all 3 machines that show up here. And there's no sort of out of the box implementation with the cell processor. We're going to have to do some hand code generation for that one. Now, if you optimize it for the NUMA memory architecture, and at least in the machines at this time, which may be less true today, added software prefetching, that was an important optimization. And it doesn't change the computational intensity. We haven't done anything to change the matrix formats here or anything like that, but it has boosted us up towards the higher bandwidth limit on each one of these machines. And then if you are looking at matrix compression, that is using things like register blocking, then you can improve the instruction level parallelism. You can also improve the computational intensity as well. So that register block can be unrolled, that can give you better ILP. We have fuse multiply add throughout these, so that's not really something that had to be implemented, although you need to make sure the compiler can generate it based on that inner loop that had an index lookup inside of it. And so when you do these other optimizations, you can see that you've improved the performance again on each of these systems. And now we finally have an implementation of the cell blade processor, which is doing pretty well. And but all of them are now doing better. They're still bandwidth bound, right? They're still in the bandwidth limited part of the roofline model, and all these systems not in the compute bound part. But that's not unexpected because it's matrix vector, and moreover, it's sparse matrix vector. So that was a dense matrix in sparse format. I should have said that before in that roofline model. So let's look at what happens with real matrices. And these are a bunch of different matrices. Again, the leftmost one is a dense matrix in sparse format. The rightmost bar here is the median across all of these matrices. There's a linear programming matrix, which is the rightmost one in the clump. And a circuit simulation matrix also tends to be a really hard one. That's the web space matrix. Those are also, these are kind of organized, easier on the left and harder on the right. And so this is the performance that you get. Again, the y-axis is the same. It tops out at 4 gigaflops. This is now a multi-core, so this is a shared memory multi-core implementation. And this is the naive code in purple. That was the serial code. This is what you get from parallelizing it. So it's nowhere close to the number of cores on each one of these systems, which is certainly more than 2 on all of them. And but if you put in a bunch of other optimizations, so things like register blocking, which is called compression here, prefetching, and the NUMA optimizations, you really boost up the performance. And then you can do things like cache blocking and TLB blocking, which I haven't really talked about it, but that also, there are a couple of these harder matrices, you can see a bit of a boost. And that sort of confirms what I said before, that unless you have a particularly odd sort of matrix or one that's very irregularly structured, like a linear programming matrix, you tend to not get a lot of cache blocking benefit. There is one finite element matrix in Victoria Falls, which was a very highly multi-threaded, it kind of looked a little bit like Knight's Landing sort of processor. That one had some benefit as well. And there's the sort of best case overall of these optimizations and the speed up that you get from all the different optimizations. So you can get, well, 35x only because, you really couldn't do anything at all on the Blade processor. But even for these more traditional hardwares, you can get up to say 4x on but from doing a series of optimizations. All right, so, and probably the last thing I'll do, let's see how time goes, is talk a little bit about communication avoiding. So when we talk about CA here in this class, we tend to use communication avoiding iterative solvers. So now we're going to look kind of up a level what happens in the context of SPMV within a higher level iterative algorithm. So this was a plot that Rich Vudik did many years ago when he was here as a grad student that I think sort of changed our thinking about what we needed to be doing. So at the time we were working on OSCE, we were working on, he was building OSCE, we'd already had, Yunjin had done the sparsity project, we'd had a lot of work on register blocking, cache blocking, things like that. And what this was saying is that if you look at a few different processors at the time, most of the time was spent actually in transferring the data from memory. So this kind of dark red at the top here is the time to just, from a bandwidth perspective, read the matrix from memory. And so what that says is, yes, do all of the things that Sam talked about, register blocking. Well, that's compression, so that can help you a little bit but prefetching and NUMA optimizations and stuff might make more effective use of your bandwidth limit of the machine, make more effective use of the bandwidth, but you're going to end up eventually being bandwidth bound. And we were, after having spent a few years working all these different optimizations, we were pretty clear that we were now bandwidth bound once you have a well-optimized code. So you may have a factor of 2 or 4 or something to get to this bandwidth limit, but once you're at this bandwidth limit, there was sort of nowhere else to go, because you have to read the matrix. Okay, so, we can compress things. One of the optimizations I didn't mention is using smaller index types, things like 16-bit indices, where you kind of have a local index, things like that. So there are ways of compressing them, but for the most part, you've got floating point values in there. There's not too much you can do to compress the actual data in the sparse matrix. So what are we going to do about this? It's very important for a lot of different iterative methods. It comes up in both in data analysis problems, it comes up in simulation problems, but we have just these 2 flops per non-zeros. So we want to look up the next level in the stack, what algorithms use SPMV, and can we reorganize those to avoid communication, basically because I already told you that these algorithms are going to do multiple SPMVs. So that's really the hint here. So let's look at a class of algorithms called the Krylov subspace methods. This includes things like conjugate gradients, GMRes, Lanczos, and other algorithms where we're computing a bunch of different vectors based on a sparse matrix vector multiply. We do a series of, say, k of these SPMVs to get these k vectors, and then we're going to find the best solution as some linear combination of those k vectors. So at a very high level, and Jim talked a little bit about some of these solvers when he talked about structured grids, but we can, and in the sources lecture, that's roughly speaking what they're going to do. So we've got a number of SPMVs all using the same matrix A. So that's really important. And so the goal is to make the communication cost independent of this K, rather than doing, say, in the kind of traditional case in parallel, where we have to send log P messages and say our reduction operation for SPMV, where we don't want to send k times those. Can we instead send just log P of those rather than k times log P of them? That is one log P message for each step. And so with the same bandwidth as before. And in the serial case, the question is, can we actually, rather than reading the matrix k times and therefore incurring that k bandwidth, can we read the matrix once and get and use it k times? And the answer is, kind of roughly speaking, this is going to be something we can do when the matrix is something that can be partitioned pretty well with a low surface to volume ratio. So Jim talked about this example in structured grids. I'll just run through it quickly here. But what we have is our x vector as input, then we're computing ax, a squared x, and so on. This is a tridiagonal matrix, right? We're doing nearest neighbor computation on this one-dimensional mesh, if you will. And we are, so we've got a dependencies that look like, look at 3 of the values to compute the output of the next one. And so after a couple of steps, we can end up, we can build this output vector, an a cubed of x, if we've got a wider input vector here with k extra things on each side. And this is what our sparse matrix looks like here that we're computing. And so we can use this, but for both the serial case, where we can sort of stack these parallelograms together, because in the first step we had this trapezoid which got sort of chopped off here, but then on the next step we can reuse what we've computed there, but then on the boundary, but then compute everything else that is based on the input value of the bottom of the blue. And in a parallel case, it was, he talked about the fact that it's a little bit more complicated. And one of the things that you can do is to do redundant computation, where each processor is really computing a trapezoid. But for example, processor 2 is computing the green, the orange, and the yellow parts. So it needs the input from this wider vector in order to get the output. Let's say that it owns these yellow points at the top. In order to get the input, it needs some stuff that's from processor 1 and processor 3, and then it's going to do some redundant computation. And it can be traded off in various ways. But that's by far the easiest case, right? That's where our matrix is a tridiagonal matrix. So what if we have a general SPMV and a general matrix? How can we do this communication avoiding idea? Well, if a processor owns a piece of the matrix and a piece of the vector, that's really what it means, is it owns in the graph form of that sparse matrix, where the edges are the non-zero values in the matrix, and the vertices here are the vector elements that are coming in and then being computed on the way out. So we're going to be, let's say that each one of these is some element of y, these black dots. And so some processor owns this chunk of things, and we've carefully chosen a chunk of things that are contiguous in the mesh, in that graph structure, right? So that it doesn't have too many nearest neighbors. And then in order to compute a times x for all of these input values that are inside of here, we'll also need the neighboring values in the mesh. So we'll need these neighboring red vertex points. Those are the inputs of the x vector. And we're also going to need the matrix values that are the edge weights on there. And similarly, for a squared of x, we'll need two hops away. And for a cubed x, we'll need 3 hops away. And so we can do this, and we can save communication if we can reasonably partition the matrices. And so we can change our memory bandwidth to O of 1 bandwidth for rather than O of k bandwidth. And we can change our message latency from k log p to log p by using this kind of a trick. But there's a whole bunch of stuff behind this, and this is a paper by Margub Mahoiden and Mark Homan and Jim and me from a number of years ago, looking at how to optimize this kind of algorithm. And they used hypergraph partitioning in order to get this sort of partitioning of the matrix. And then still, because of the fact that you don't really control the cache hierarchy explicitly, then lay things out using a traveling salesperson problem for algorithm to lay out the matrix and minimize the number of cache misses. And these are the kind of speedups that they get from the red is the original running time. This is a gigaflop rate. And the A to the K is referring to the fact that you're doing these A to the K kernels, these matrix powers kernels, rather than just doing a sparse matrix vector multiply. And so you can see a substantial speed up on something like a 1D 5-point stencil. So that's similar to what Jim talked about, although what we were showing here was a 3-point stencil in 1D. Obviously, a 1D mesh is really easy to partition, so that is the best case. And some of these harder things then have a lower speed up, but still a substantial speed up. And here's some of the kind of speed ups that you get overall. You can see 6x on the Cloverton, that Intel Cloverton that I mentioned, a multi-core system. And if you are actually looking at what we call an out-of-core algorithm, and I think Jim also mentioned this idea that back when memory, rather than being DRAM, was core, we sometimes call things that were kind of moving data to and from disk an out-of-core algorithm. So you can get a speed up from that as well. And a sort of modeled petascale machine at the time, what that model looked like, and a grid speed up. So that means running something across, say, multiple sites in distributed across multiple HPC systems would be a grid computer. And there you can get really huge, much larger speed ups. And so the sequential speedups are really in bandwidth improvements, and the parallel speedups tend to be really more from the latency improvements that you're getting. There's a lot of numerical algorithms work behind this for the other, for all of the different Krylov subspace methods. And it's in both Mark Homan's PhD thesis under Jim and also Aaron Carson. So you can look at those PhD theses. And there's other papers on the Bebop website if you're interested in doing this. And they basically, these are the same sort of model speed up numbers, removing this factor of K in both cases that I've talked about already. But it does change the numerics. So, and that's really one of the things I wanted to talk about. So I'm not going to read through this slide, which has got sort of a pseudocode for GMRes here. And GMRes is it was one of the first algorithms done in Mark Homan's thesis, and probably one of the simpler algorithms in terms of the numerics. But you've got standard GMRes on the left-hand side and a communication avoiding version on the right-hand side. And without reading through all the code, I'll just say on the left-hand side, you're doing a matrix vector product, sparse matrix vector multiply A times V, I minus 1. On the right-hand side, you're computing this set of matrix powers kernels, A squared V, and so on. And then there's also something else that changes, which is actually very important in terms of the speed up, which is there's some other work, which is the modified Gram-Schmidt algorithm, which turns into a TSQR, a tall skinny QR factorization here on the right-hand side. And so that also changes the some of the collective operations that are done in the code across the processors. So if you do that from a kind of a pure compiler standpoint, I would say what I'm doing is sort of inverting some of these loops. So taking these, taking this for loop and putting it inside of the matrix vector product and so on, so that you're getting these different steps. But and you are actually preserving if you were doing this in pure real arithmetic, if you had a real arithmetic machine, which we can't build, then you would have, you would actually get the same result. This is what happens to the error. So the y-axis in this case is the relative norm of the residual error, AX minus B. And this is the original GMRes, which is doing what you want it to do, which is as you iterate through the algorithm, you're reducing the error. So you're getting closer and closer to the exact answer. And what happens if you do the communication avoiding algorithm sort of out of the box is, which is using what's called the monomial basis, is your algorithm no longer converges. And so these green triangles here show you your error, and not only is it high, but it's not getting any better over time. And so we're really not making any progress here. But fortunately, by also understanding what's in the numerics, you can replace that basis with what's called a Newton basis. It still uses those that matrix powers kernel, and it still uses that TSQR, and you can then regain the convergence back from that. So the point is, you do have to think, if you're looking at something that's memory bandwidth bound, like sparse matrix vector multiply, you may be able to optimize at a higher level, but you then have to really worry about the numerics at a higher level as well. And this is the performance again on that Cloverton system for the matrix vector multiply. Sorry, with the matrix powers kernel for this communication avoiding GMRes. Okay, and I don't really have time, I think, to do sparse matrix multiply, or matrix times a set of dense vectors. I will just say there's a lot of other interesting work in here, and is something that may be of interest to you in a final project. There's some work by Penporn Koanantakul in her PhD thesis looking at a bunch of different algorithms for sparse times dense matrices. The shape of the matrices and the sparsity pattern really matters. I think Alok may have talked about this a little bit as well. And there's ongoing work in some of these kinds of problems with Aiden and a number of other students and postdocs. But she did this kind of communication avoiding ideas for this sparse matrix kernel, and then put it into a machine learning algorithm called HP Concord and then applied that to this brain imaging data. So this is for inverse covariance matrix estimation, this HP Concord. And if there is somebody who's interested in that, we can certainly point you to the papers, and would be happy to even put you in touch. I'm sure Penporn would be interested in having people look at that inverse covariance matrix. So it's computing a graphical model. It's a graphical model estimator. So, but I just wanted to end by talking a little bit about other class projects in here. So you can certainly do a very experiment heavy final project in which you're looking at a number of different architectures and different matrices for things like SPMV. And you could possibly update Piasky, although that's a larger effort. You would definitely want a large team if you're going to do that, and you have to be comfortable modifying other people's code, but making that sort of updating that for modern systems, because we haven't really dusted it off recently. You could look at particular matrices of interest. So if you are interested in a particular problem domain, there was this communication avoiding algorithm idea was used in an adaptive mesh refinement problem, and in what's called the bottom solver. So kind of at the bottom of the adaptive mesh, when you turn something into a sparse solver, it was able to speed up that bottom solver substantially. Exploring the tuning space of things like the matrix powers kernel, and looking at code generation frameworks such as Halide or SPF for generating optimized auto-tuned code, and other sparse matrix operations besides matrix vector product. So I think with that, I am exactly on time. Let me just make sure there are no questions. I think there was just a comment from Jim in the chat. So I think with that, I will end. I'd be happy to talk with people during office hours about project ideas. I think both Aiden and Jim, I'm sure, would also be happy to talk about things, especially on the numerical algorithm side. You should probably talk with Jim, but in terms of sparse matrix optimizations, all of us are interested in those as well. So thanks very much. I think I wanted to make sure people know that homework 3 is being released later today. So if you didn't see that in the chat at the very beginning of lecture, there'll be an announcement on Piazza. So make sure you don't miss that. Next week is spring break, so we won't see you here in lecture. And I hope you all have a chance to get a break in terms of taking some time off from classes and things like that. But we will be around and monitoring Piazza and things like that off and on during the week. Thanks a lot. We'll see you in a little over a week.